Welcome to the deep dive. Today we're getting into something that feels, well, pretty simple day to day, but is actually incredibly complex underneath, making buildings comfortable.
Yeah, we all just, fiddle with the thermostat.
Right. But figuring out the exact heating and cooling a place needs, that takes us deep into physics, materials, even the sun's path.
It really does. It's a serious engineering puzzle. And for this exploration today, we've gone straight to a key resource for folks in the building world, the ASHRAE Handbook.
That's our source material. We're going to unpack what these, pretty technical sources say about calculating those heating and cooling loads,
Yeah.
what makes houses unique here,
Uh,
and then we'll really zoom in on something huge, windows and doors,
Yeah.
or fenestration, as the handbook calls them.
Great fenestration.
Yeah.
Our mission really is to sift through all this detail, pull out the key stuff, maybe some surprising bits, and help you get a handle on the core ideas behind designing for comfort and energy efficiency.
Okay, let's jump in.
Let's do it.
So, residential buildings. What do the sources say makes them different when we're talking HVAC loads?
Great place to start. So, the handbook points out that homes, unlike big commercial buildings, offices, shops, they're usually lived in and conditioned 24/7.
Okay, constantly running, basically.
Yeah, and the big thing is what drives the heating and cooling. It's not usually loads of people inside or tons of lights like you'd find in a crowded office.
Right, the heat from us watching TV or the kitchen lights, it's pretty small compared to...
Compared to the heat moving through the building itself. The walls, the roof, the floor, and critically, how much outside air leaks in. Infiltration, they call it.
Infiltration. So the building skin, how leaky it is, that's the main story for houses.
That's the core of it, yeah. The building envelope, as they say.
Makes sense. It's either holding the heat in or letting it flood in.
Exactly. Now, for the cooling load, how much heat you need to remove, you're adding up all the ways heat gets in. So heat through the walls, floors, ceilings, heat blasting through windows, heat from those air leaks, and then the smaller bits from people and appliances inside.
And the sources talk about sensible heat, like just temperature, versus latent heat, the moisture,
Right.
handling them separately.
Correct. They're calculated distinctly. And it also notes that even if you have one central AC for the whole house, doing a room-by-room breakdown is often best practice.
Why is that? For sizing things correctly.
Yeah, to make sure you size the ducts right and get enough airflow everywhere. You don't want one room freezing while another's roasting.
Good point. Okay, so this leads to something you mentioned sounds a bit counterintuitive. Heat gain versus cooling load.
Yes. This is a really key concept from the sources. Instantaneous heat gain, that's the heat pouring into the building right this second, isn't always the same as the cooling load, which is what your AC actually needs to deal with.
Wait, how could that be? If the heat's coming in, doesn't the AC just fight it?
Well, think about the building materials themselves. The drywall, the wood framing, maybe a concrete floor. They have mass. They can absorb heat.
Like a sponge.
Sort of, yeah, a heat sponge. They soak up some of that incoming heat energy, especially during the peak sunshine hours, and they don't release it into the room air immediately.
Okay. So the building itself is kind of buffering the heat.
That's a great way to put it. It buffers it. This does two important things to the cooling load. It delays when the peak load hits your AC system, often pushing it later in the day,
Right.
and it also tends to flatten out that peak. Makes it less intense than the absolute maximum heat gain happening earlier.
Wow. Okay, so the structure itself helps smooth things out. The AC doesn't have to react quite so violently the moment the sun is strongest.
Exactly. And, the sources go into the different ways engineers have tried to model this effect over the years, these
Yeah.
different calculation methods.
Right, you mentioned those acronyms, TFM, CLTD.
Yeah, transfer function methods, CLTD, SCL, CLF, TED, DTA, radiant time series. It's a whole alphabet soup.
Huh. Sounds like it.
They represent, decades of work. Some are really complex, need computers like TFM. Others were developed earlier, simplified for doing calculations by hand, like the CLTD or TETD methods.
Before we all had powerful computers on our desks.
Right. And the sources are honest. They say even those simplified ones have, weaknesses in perfectly capturing how that thermal storage really works. It's tricky stuff.
That makes sense. Let's switch gears then. Heating loads. How are they different?
Generally a bit more straightforward in one key way. When calculating how much heating you need, engineers typically don't give you credit for any heat you might get from the sun shining in or from people inside.
Ah, so no free heat counted.
Pretty much. The idea is if heat is leaking out through the walls or windows when it's cold, you need to replace it now to stay warm. It's treated more instantaneously.
Need the heat immediately. Got it.
And while the outside temperature is obviously the main driver, the sources really stress how important wind speed is for heating.
Wind. Why wind?
Because wind drastically increases infiltration, those air leaks we talked about. It forces more cold outside air into the building through all those tiny cracks and gaps.
So a windy, maybe not that cold day could actually be worse for heating than a dead calm, but much colder day.
It absolutely could be. The worst case heating need might be a specific combination of temperature and wind, and it varies depending on how airtight the house is and the local climate.
Interesting detail. And what about pickup loads? What's that?
Yeah, that's for buildings where people turn the thermostat way down at night or when they're away.
Like a setback thermostat.
Exactly. When you turn it back up, the heating system needs extra power, not just to warm up the air, but also to reheat all the stuff inside the furniture, the walls, the floors that cooled down. That extra bit is the pickup load.
Right. Got to warm up the whole thermal mass again. Okay, beyond the big envelope loads, any other heat sources or losses the handbook mentions?
Sure, appliances inside, obviously. They mention one kind of specific finding. Gas appliances under a typical kitchen hood might actually radiate a tiny bit more heat into the room than electric ones because of the hot combustion gases.
Subtle difference.
Yeah. And motors, like in fans or appliances, they generate heat. Whether that adds to your cooling needs depends if the motor's inside the conditioned space or, say, out in the garage.
Makes sense. And then ductwork.
Yeah.
That sounds important.
Hugely important. Ducts running through unconditioned areas like attics or crawl spaces. They can lose heated air in winter or gain heat in summer before the air even gets to the room. That hurts efficiency.
But the bigger issue was leaks, right?
Oh, yeah. The handbook really flags duct leakage as a massive problem.
I feel like I've heard some scary numbers about that.
The sources quote figures like 10%, even up to 35% or more of the air leaking out of ducts in some houses.
35%. That's wow. So all that careful calculation of heating or cooling needed for a room.
Right. If a third of your expensive conditioned air is just leaking out into the attic or walls, it totally undermines the whole system design. Supply leaks mean air doesn't get where it needs to go. Return leaks mean you're sucking in dusty, hot, or humid air from places you shouldn't be, making the system work way harder.
That's huge. A massive potential waste.
It's a major gap between design calculations and real-world performance. And one last point the handbook makes. Sometimes, even in winter, certain parts of a house might actually need cooling.
Really? Like what?
Maybe a really sunny room gets overheated even on a cold day, or an interior room with, I don't know, a lot of computer equipment running. Designers have to think about those specific zone needs too.
Right, you can't just assume the whole house needs the same thing everywhere.
Yeah.
Okay, let's dive into fenestration, that component the sources focus on.
Yep, fenestration, fancy word, but it just means windows, doors, skylights, basically any opening in the building envelope.
Okay, and how does energy move through these? What are the ways?
3 main ways. First, good old conduction and convection. Heat just moving through the solid materials, the glass, the frame, and through the air or gas trapped between panes, driven by the temperature difference inside versus outside.
Standard heat transfer. What else?
Second, long wave radiation. Think of heat radiating between surfaces. Like in winter, the cold surface of the window glass radiates cold towards the warmer interior walls and furniture. You feel that.
Okay, and the third one sounds like the big one for summer.
Definitely for cooling, yeah.
Yeah.
Shortwave solar radiation. This is the heat energy directly from the sun, plus sunlight that bounces off the ground or other buildings coming straight through the glass.
That's the one that really heats up a room. So the handbook gives us metrics for this, right? U factor and SHGC.
Exactly. 2 key numbers. U factor measures how well the window insulates against that conduction and convection heat transfer.
So lower U factor is better insulation.
Correct. Less heat gets through just because it's hot outside and cool inside, or vice versa. It's kind of the inverse of the R value you hear about for walls.
Got it. Lower U factor, better insulator. And SHGC.
SHGC stands for solar heat gain coefficient. It's basically a fraction between 0 and 1. It tells you how much of the sun's heat energy hitting the window actually gets through it and into the room, either directly or by being absorbed and then re-radiated inward.
So a lower SHGC means less solar heat gets in.
Exactly. You want a low SHGC, especially in climates where cooling is a big deal. And the handbook notes SHGC is the modern, more accurate way to measure this, replacing an older metric called shading coefficient. It counts for the full solar spectrum and different sun angles.
Okay, so U factor for insulation, SHGC for blocking solar heat. And these numbers apply to the whole window unit, frame included.
Yes, the whole thing: glass, spacers, gas fill, frame. The source explains how the frame material matters a lot. Metal frames can conduct a lot of heat that's called thermal bridging, unless they have a good thermal break designed in.
So the frame can be a weak link.
It can be, and these ratings also apply to doors. The handbook has tables for typical door U factors too.
Right, doors are part of the envelope too. And shading. The sources make a big deal about shading, don't they?
Oh, absolutely critical, especially for tackling that SHGC, the solar heat gain. Exterior shading is generally best.
Like overhangs or awnings.
Exactly. Or outside blinds. Anything that stops the sun before it even hits the glass is most effective.
But inside shades, like blinds or curtains, they
Yeah.
still help.
They make a big difference, yeah. And the handbook gets into some really neat details here, especially about draperies. It talks about classifying the fabric based on how tightly woven it is, the weave openness,
Yeah.
and how reflective the yarn is.
Why does the weave matter for heat?
Well, those properties dictate how much solar energy the fabric reflects back out, how much it absorbs, and how much passes through into the room. A tight weave, a reflective yarn, that blocks more heat,
Okay.
and it also affects how comfortable you feel near the window, that radiant heat aspect, and obviously how much view you get through it. The source even mentions that draperies absorb sound. It links their noise reduction coefficient, NRC, to how open the weave is.
Wow, curtains as sound absorbers. Never thought of that. And double draperies. What's the idea there?
Yeah, using 2 layers, maybe a sheer layer close to the glass for some daylight and view, and then a heavier, more opaque layer on the room side for privacy, better heat blocking, and comfort when you need it. Gives you flexibility.
Makes sense. Okay, so beyond just heat flow, what else does the handbook cover regarding fenestration?
Daylighting is a big one, using windows to light the space naturally, so you use less electricity for lights. They mention rules of thumb architects use, like aiming for window area to be around, say, 20% of the floor area in the US, ballpark.
Right, natural light.
And they discuss spectrally selective glass.
Ah, that's the stuff that tries to let the light in but keep the heat out.
Precisely. It's designed to be transparent to visible light, but reflect or absorb the invisible infrared sheet energy from the sun. Maximize daylight, minimize unwanted heat gain.
Clever.
Yeah.
Any downsides?
The sources mentioned there can sometimes be trade-offs, like maybe a slight color tint to the light coming through. And there's this idea of a forbidden zone on performance charts, basically. Combinations of highlight transmission and super low solar heat gain that are just physically hard to achieve with current tech at normal sun angles.
Right. And it all comes back to people feeling comfortable, right?
Absolutely. Occupant comfort is paramount. The handbook references ASHRAE Standard 55, the main standard for thermal comfort. And for colder places, it specifically recommends double glazing if the winter design temp is below about 7 Celsius or 45 Fahrenheit.
Why double glazing specifically?
To reduce cold drafts near the window, make it feel less cold radiating inward, and crucially to prevent condensation on the glass when you have normal indoor humidity levels. High-performance windows can seriously cut down cooling loads compared to old single panes too.
And windows need to last, obviously. Durability.
Yep, mentioned too. Things like test for the seals on double or triple pane units, insulating glass or IG units. If you see fogging between the panes, that seal has failed.
Right, the dreaded foggy window. And finally, strength. Safety.
Windows have to stand up to wind pressure, of course, but the sources also flag something called thermal stress breakage.
Thermal stress.
Yeah, when one part of the glass gets much hotter than another part, like if the sun hits half the window but the other half is shaded by an overhang, or even if an HVAC vent blows cold air directly onto a section of hot glass.
That temperature difference can actually break it.
It can create enough internal stress to crack the glass. And they note that some glass types, tinted, reflective, low-E coatings, can actually be more prone to this than plain clear glass because they absorb more solar energy.
Wow, something to watch out for.
Right.
Okay, let's pull this all together. Why does understanding all this detail about residential loads and fenestration matter to someone listening?
Because those windows and doors, they aren't just openings, they're dynamic parts of your building's energy system, and they massively impact your comfort. They're properties that you factor, the SHGC, how good your shading is, they feed directly into those load calculations we talked about.
And those calculations determine how big your furnace or AC needs to be, right? How much it costs to buy, how much it costs to run.
Exactly. If you understand fenestration and account for it properly in the load calculation, you might be able to use a smaller, cheaper, more efficient HVAC system. You get lower energy bills, you get a home that actually stays comfortable.
And if you ignore it,
You risk getting an oversized system that cycles on and off too much, doesn't dehumidify well, and wastes energy. Or maybe worse, an undersized one that just can't keep up on the really hot or cold days. It's fundamental to getting the design right.
so we've really dove into the technical side here, based on the ASHRAE Handbook, looking at how we figure out residential heating and cooling needs, and especially how critical windows and doors fenestration are in that whole equation, from thermal storage in walls to the weave of curtains.
Yeah, we've seen how many factors engineers juggle to try and predict how a building will perform based on materials, climate, all those things.
Okay, so here's a final thought for you to ponder. Engineers use these incredibly detailed methods, all these tables and calculations, to predict building performance based on physics and design choices.
Yeah.
But the comfort you actually experience in a room is also shaped by things calculation can't easily predict, right?
Like what?
Like, do you actually remember to close the blinds on a hot afternoon? Where you put your heat-generating TV or computer? What about the shade from that tree that grew bigger than expected, or the heat reflecting off your neighbor's new extension?
Ah, the human factor. And microclimates.
Exactly. How much of that messy, real-world, human-influence stuff can the calculations truly capture? And where does good building design need to leave a little room for error, maybe some built-in flexibility, or just rely on some well-informed guesswork to make sure people are actually comfortable in the end?